my first slide is what is STXM? Scanning, transmission, X-ray, microscopy. So here, first you see an overview of what we have in the end station. So in principle, there's a whole beamline attached to it, but for the sake of simplicity, the beamline just gives you monochromatic X-rays when you get to the end station. So in the end station, what we have is a focal element called a Fresnel zone plate. They are very small. So on average, they have like a diameter of 300 micron. And they are made up of gold usually, or sometimes nickel or other materials, iridium, in small circles with raised sort of profiles on them. And what they do is they focus the beam, they diffract the beam into a small spot. This is the green beam that you can see is the orders that we want. So that is the actual focusing that we want. But obviously, it being diffraction, it also has multiple orders that go elsewhere. So in between the focal element, the Fresnel zone plate, and the sample, we also put an order sorting aperture to block everything that is not this first focal beam that we do want. And you can see on the zone plate, also the middle bit is taken out, because what you typically also get is beam that is not diffracted by the Fresnel zone plate. So the middle section would then be a beam that is not diffracted at all. So both that and the other orders that you don't want get blocked by the central stop on the zone plate, and then the rest by the aperture. So by the time we then get to the sample, what we have is a couple of tens of nanometers size spot. So typically 20 to 60 nanometers in diameter, a round spot on the sample. And then we move the sample through the beam and take in each spot that we illuminate, we take the intensity of the light that comes through. So basically, we do a pixel by pixel representation of what we get. Right. Then what we get is one image, because we have one energy, we have monochromatic X-rays, and we have mapped out the intensity that comes through our sample. So obviously what you get is where there is a sample, where there is something on the plate, let's say, less light will be transmitted, so it will look darker. And places where there is not something will be relatively intense and white, because that is where the beam just basically travels through unhindered. And we use that as a calibration. So if you have empty bits on your sample area, then we call those I0. And the transmitted beam is whatever goes through your sample, and therefore intensity is taken out because X-rays are absorbed by your sample. So this is then a pixel by pixel image that is built up at one energy. And of course, what you can then do, because you're at a beamline, is you can change the energy slightly of the incoming light. And then usually, or hopefully, what you will see is that the image changes slightly, so that there is darker and less dark regions that switch between energies, because different things absorb light differently. And not enough with that, you can of course change it again and again, and build up an entire stack of energies, usually around a particular energy region that you have chosen with a good reason. So what you do, namely, is that you take an edge of an element that you want to study. Like, for instance, you want to look at iron in your sample. So then several textbooks will tell you that around 707, 708 electron volt in the soft X-ray regime, there is an X-ray absorption edge for the iron, namely the L edge. And that it can therefore tell you whether there is iron in the sample if you scan from below that edge to somewhere above that edge. And this is then what you can do. And not enough with that, if you see that in your stack of images, there are certain areas that behave slightly differently than other areas, you can pick those together in the data analysis program afterwards and say, okay, give me the spectrum over all of these pixels, over all of these energies, and tell me what it looks like. And if you then indeed search for areas that look similar, then you can map out different spectra. You can do this by yourself, just by eye, but you can also use principal component analysis, so to let the computer test for you which areas are similar, which can be grouped, which pixels can be grouped, and so extract spectra. You can even, of course, do it for single pixels and map out the spectrum for each single pixel, but typically that would be a bit more noisy than this. Right, then what do? Well, you can normally compare them to references. So if you are looking, for instance, at the iron edge, you may have some inkling that you're looking for different oxidation states of the iron in your sample. For instance, Fe2+ and Fe3+. And then you can have references from like Sigma Aldrich that you prepare on a similar sample slide, and you run through them as well, so that you know what an Fe2 plus spectrum would look like and what an Fe3+ spectrum would look like. And then you can compare them to what you find in your actual sample. Again, you can do this by eye, just qualitatively, saying it's like, well, the top one kind of looks like Fe2+, and the bottom one is much more like a mixture of the two. But you can also do it by fitting or, again, some sort of like more advanced data analysis. But in a nutshell, this is then how you find out what is going on in your sample. And you can plot it in the end by saying it's like, okay, where is now my Fe2 2+? And you can have it in sort of like a quantitative way, this being the quantitative scale of like nothing at all to very much. And of course, you can put numbers on that. But you can plot it to say, like, this is the Fe2+. In an Fe3+ image, these areas would maybe be more lit up. And what is represented here, as you can see, it is sort of the opposite of what we have here, right? What is here white, because there was no absorption, is now black. And that is because what we typically plot is this quantity, the optical density, calculated in this way from the original images. So this is basically what STXM can do for you. It is microscopic imaging with X-ray absorption contrast. So I've shown it to you here for the iron edge, but you can do other edges as well. We do cover the carbon edge, the nitrogen edge, the oxygen edge, the calcium edge, you name it, we cover quite a lot. And for all of these edges, you can get chemical information on a 2D submicron scale. So this image would be typically something like 5 by 5 micron, maybe. And the pixel sizes that you would do, you would match to the kind of resolution scale that you need. So maybe 30 nanometers or 100 nanometers, depending on what you're looking for. Moreover, as I said, these colors, they come with actual numbers. It's quantitative chemistry. And the sensitivity of the STXM method is roughly between 1 and 10 milligram per gram for the different edges. So it differs a little bit which edge you look at. Calcium, very sensitive. But other elements like sulfur, for instance, are less so. In comparison to other techniques that you may know, we can have a look at the spatial resolution versus the chemical content. And you see that we occupy a nice niche in the middle, where, like, of course, you can have better resolution with some of the techniques like STM or TM even. But the chemical contact, the chemical information that you can get from it is much better in STXM. On the other hand, IR, for instance, can give you quite good chemical information, but usually the resolution is not so good unless you do AFM IR, but it's a different story. Right, so this is in a nutshell how you should think about STXM. It gives you chemical information on a 2D submicron scale. 3D is possible, but it's cumbersome. Right, then SoftiMAX. What do we do? Well, we are a beamline that covers an energy range from 275 to 2500 EV for the STXM branch, and that covers all of these edges that you can see colored in the system. So as you can see, it's quite a lot. So a number of them we cover in the K edge, other ones like iron, for instance, in the L edge, and even other ones in the M edge, so the 4Fs, for instance. So that is what we can do, notably. Chlorine, don't ask me about it because we don't cover it. How does it then look inside our end station? Well, typically, this is what we have when you look in from the side. So by now, maybe the beam is coming from the other side. So the zone plate is mounted on the very end here. Here is the order sorting aperture sticking nicely in between the two. And then the sample plate, this massive thing with the sample. And then the detector, this you can just see the tip of it, is behind here. Now, this distance from the sample to the zone plate is a couple of millimeters, right? So, and again, this distance to the detector is also a couple of millimeters. So we don't have a lot of space, which typically means that your samples have to be thin, and that also the sample plate, like here, and we have those at the beamline. So if you want to mount the samples, we have all of that. It's just that obviously you need to be able to put your sample on this, so you can't make anything super big. And what we typically recommend is silicon nitride windows. They can be either 5 by 5 or 3 by 3 in this sort of like outer region, and the window size up to 1 by 1 millimeter in size, or TM grids. And then with that, we can say thin samples is the norm, as said. Soft X-ray, everything is very close as well. So typically 100 nanometers or around this is used for the lower energy, so the carbon, for instance, and you can go up to a couple of microns when you get to the higher energy side of the beam lines, which also means that if you want to combine edges, right? So if you want to combine something that is at the lower energy side with something that is at the higher energy side, you might need to make more than one sample, right? Because otherwise you might not either get enough contrast, or if you have very thick samples in the low energies, you might not get through. The best resolution that we have for actual samples, more than just a proof of principle, for actual samples is 20 to 60 nanometers. But it is not something where you would say, it's like, of course, give me the best resolution. Think about what you need. Sometimes 50 nanometers is enough for what you want to see. So that is perfectly fine. The sample carry, as said, silicon nitride, TM grids, and the window thickness. Typically, what we tend to use is 50 to 100 nanometers thick. If you're not very used to working with these ones, I would go for the slightly thicker ones, simply because they are fragile and it's easy to break. And for the TM grids, think about the material. So if you want to study the copper edge, maybe having copper TEM grids is not the best choice. And the pore size, right? So again, you want to have a fairly open spaced grid, but obviously it still has to catch whatever you try to do. And we've had this very unfortunate event once before. With the grid, we cannot look through the grid, right? We have to look through the pores. So the sample has to be in the pore, not on the grid. It's very important to keep in mind. What we can also do at the beamline is tychography. It's a somewhat related technique, which I'm not going to go into, but it is generally for samples that are scattering. So it is very heavily used in magnetism, but anything that is a little bit more, not very smooshy, let's say. It can help with increasing the resolution, but it comes with the cost of being slightly more difficult with the data analysis. We also have the possibility to work with magnetic and polarization contrast in your samples by changing the polarization of the light that we have, so the polarization of the photons, if that is something that you would need. And for this specific application round, we do room temperature only. We are waiting for our cryo setup. And also because, as we said, we are running a little bit late with our STXM rebuild, and we wanted to keep something that we could definitely ensure. We don't bid for elaborate sample environments this round. That will have to wait one more. Right, then the proposal for Max 4, as said, the call for proposals is open until next week, Wednesday, I think. And when you make an account on the system that we have called Duo, and you download a template for the proposal, it asks you for the following information. So for the goal of the experiment, I have here just an example of one of the the proposals that made it in the last round. So this is just basically stating very, very shortly in one small paragraph what you want out of the experiment and why sort of like, STXM might be a good choice. And as you can see here, he wants to map iron 2+ and 3+ inside sort of like, very precisely prepared samples from, in this case, lung tissue. So, I mean, that is very, very quickly stated. The scientific background, I leave to you. You should know what you're studying, so I'm sure that you can do a good job in describing that. What we want from the experimental methods is a bit of a layout of the experiment that you want to do. So for STXM, how many samples do you need to measure? How many regions, how many edges, in effect, do you want to measure as well? So sometimes you need more than a couple of areas for statistics, for instance, especially if in the medical field, reproducibility and so on might be something that you need to show. But think about how many elements, how many absorption edges, how many regions within one sample do you want to do, and then how many samples in total. And then if you know anything about the size of the features you're after, put it down. So I mean, if you want to look at something subcellular, it will tell you something about the resolution requirements. And it doesn't have to be exactly 20 nanometers, right? I mean, it is fine if you say like, well, we want to look something at, as long as it's submicron, because otherwise there are other techniques you might want to pursue. And then if you have any information about how you prepare the sample, because that would give us a hint of your sample thickness, which, as we showed, is very important depending on which edges you go for. So if you want to do carbon, tell me that you know that the sample has to be between 100 and 200 nanometers, and you can do it with your sample preparation. We have on site an ultratone, so with a trained person to operate it. So if you need sample cutting down to that kind of like thinner thicknesses, that is available. And if you have something where you drop cast or so, that is also fine if you can have a bit of control over the thickness of the samples. The results expected and the impact on the field, again, clear, that would come from you. What does it mean? And then the relation to previous measurements at max or other synchrotrons, again, if you have, state it. If you don't, also okay. And then we come to the justification of the beam time that you need and the beam line that you need. So basically, again, it's an iteration of the resolution requirement. The photon energy range, is that a match for SoftiMAX in my case? But if you apply somewhere else, then of course there. And then the timing that you need. So Max 4 is one of the ones that works with one shift is 4 hours, which is unusual. So keep that in mind. And then usually for the STXM, you can ask anywhere between 2 and 5 days, which I'm just saying this is the norm. But I mean, anything above 6 you would never get. So that's easy. And it depends a little bit on complexity. Mind you, not the amount of samples, because we would just say like, okay, it's just not reasonable if you want to do 100 samples. But this is sort of the thing to aim for. So how do you then calculate that? Well, if you think about it, that the best resolution will set something in your step size, right? So I mean, we do the images pixel by pixel. The field of view, so if you want to look at some smaller area inside a cell, for instance, or inside a larger structure, you may want to have a bit of an overview of the larger structure. So at maximum, I would say like something that is workable is 10 by 10 micron, but it can be smaller, like 5 by 5 or 2 by 6 or whatever. The typical time that you would spend per pixel is 1 to 5 milliseconds, depending a little bit on which edge you are imaging and the abundance of that element in your sample. So if it's a very rare element in your sample, of course, you'd have to measure a bit longer. The typical number of energies that you do per stack, so I mean, if you do over an X-ray energy edge, can be 50 to 100. And therefore, if you do a full stack on one area on your sample, that could easily take between 1 and 4 hours if you do some of this averaging. So that would mean that one area, one edge on one sample will take you somewhere between 1 and 4 hours. And then you can have an idea that is already one shift, right? I mean, if you take the upper limit here. So put together some reasonable guesstimate of what you will need, and put a little bit of slack, because you might want to change samples, and of course looking around on your sample to find the right feature, plus the alignment and stuff, it takes a little bit of time as well. References, again, clear, I guess. So for the proposal, the templates are available. The system that we have at MaxForce is called Duo. What we ask of you is 2 pages, so it's not that much. And the figures, if you have, for instance, supportive data, can be uploaded separately. And then talk to us, because if you're not sure about how to set up the experiment or to justify, or you just say like, well, this is what I calculated, does that sound okay to you? Then just send us an email and then say like, this is what I'm thinking, would that be okay in the proposal? Because what happens next after the proposals are submitted is that we at the Beamline, we first have to see, is this a feasible experiment? Is somebody asking for something that we can actually deliver? So that is the first check, which is called a technical feasibility check. Sometimes we may come back to you for questions if we are not understanding what you want to do, or if it's unclear that you can make the right kind of sample for this. For the scientific evaluation, to see whether the experiment is interesting from a scientific perspective, it is sent to the proposal advisory committee of Adam. Adam Hitchcock was a part of that until the last round. So he and other colleagues, normally sort of like 5 people, they judge, you could say, the ranking of the proposals with respect to each other. Sometimes it's really comparing apples and pears, because how do you compare a magnetic experiment against a medical one? But they try and do their best to see how much, you know, for instance, the results and the scientific background is giving in terms of, like, you know, if we give you this beam time, what would it give us? And if you get a yes, we do the scheduling and you get invited to come, and Adam will tell you how to plan the experiment. And if you get a no, then there is still the possibility, especially if you're a first-time user, to try and ask for fast access. So that is a 1-day test to see something about these things, right? I mean, if you, for instance, get flagged down on the fact that you didn't describe well enough what you want to do, or that some of these numbers didn't really add up, you can say like, okay, give me one day to prove to you that we can do this, and this will be an interesting proposal. So that is a thing to take after, for instance. Right, I will stop speaking now because that's been long enough. Thank you. Do we have any immediate questions? Don't be shy. No? Okay. Then, Adam, do you?
Okay, yeah, I will start sharing my screen.
Mm-hmm.
Okay, let me see if I can clear this guy. Oh, it's doing. So, welcome to this workshop or session to inform you about STXM. As Karina says, I've been involved in this probably not as long as when I was 5 years old, but quite a few years, about 30 years. And I had a fair bit to do with expanding the capabilities. So in this session, what I would like to do, or I've been mandated to do by the AIDA team, is to give the sense of the steps that myself and my group take as we are preparing for an experiment. And I'm going to basically have a couple of slides where I have some general themes on the left side and then try to fill it in on the right side, if that's going to help orient you on what I'm doing with the talk. So I thought it might be easier just to describe a experiment that we've actually been working on for about 3 years. And one of the early successes was the experiments that were done at Max 4 2 years ago. And that is to characterize the nature of the electrochemical reactions of a zinc manganese dioxide battery and how they fail. And this is in the context of improving batteries for grid storage. So lithium-ion batteries are fantastic for this, but they're very expensive. And as we use all of the rare materials for both transportation and grid storage, things are getting tighter and tighter. So if we could have cheaper but as effective batteries, that's the goal. And so when we came into this project, I'm working with a group of Drew Higgins, a colleague in chemical engineering at McMaster, and he's got a whole team of about 4 people working on this system. And so the idea was how to identify how STXM might actually contribute to better understanding these batteries, which could lead to some ideas for improved chemistry, electrochemistry, and ancillary aspects of these types of batteries. So I think the scientific method is the right way to plan a STXM experiment. And so if you can, within that global context, identify very specific or hopefully specific questions that can then be tested, this is the most systematic way of moving forward in doing science. So the step of defining a testable hypothesis, in this case, if you look at the literature, there's some question exactly as to the active chemistry and electrochemistry that's going on. What is the mechanism whereby the chemical potential of the charge system can be released to create currents in external circuits, and how do you actually recharge the system? What's the chemistry involved in that? And also what's the chemistry involved in degradation? And because these questions can be couched in terms of identifying oxidation states and chemical species, in particular of the manganese species present in the batteries, this is a system where STXM is quite relevant because the manganese edge is a nice edge for STXM to work on. So having generally said we want to talk about electrochemical mechanisms, what is it about STXM that's going to give us our results? In this case, the answer is measuring the spatial resolution, the oxidation states of manganese at various conditions of the battery, either fully charged, discharged, and after a certain number of cycles through which the chemistry is gradually evolving. And based on that, we have to then design a STXM experiment to acquire this type of data. And this is where we have to really think in detail about what STXM can do. We know STXM is able to cover a number of different elements in the soft X-ray regime. The soft X-ray regime is actually extremely good for characterizing the immediate environment of elements because the intrinsic resolution in terms of lifetime is very good, and it is well matched by the properties of the beamlines that are used for STXM, and the sensitivity to different chemical states is actually much better in most cases as compared to, say, the K-shell edges of the 3D transition metals, which are not sensing the d electrons, which are where the active oxidation state changes are happening. So one of the things that's important when you go into a project is how much background information you might need to acquire in order to really speciate, to identify the species present. And fortunately, in this particular project, we had already, one of my students was focusing on manganese oxides for supercapacitor materials and for an in situ manganese oxide electrochemical studies. So we had actually, as part of that, made quite a detailed studies of the various manganese species that we might encounter in this study. That's not always the case, and such studies can easily burn up a whole proposal time. So that's one thing to think about. Scour the literature before you enter into a STXM project so you don't reinvent the wheel. You may have to check the actual energy scales. Often the data in the literature may be correct, but incorrect as to energy scales. So it's something to be conscious of. There are a number of ways of acquiring some data. You can do electron yield, you can do fluorescent yield techniques, which sense different parts of the material, the surface or the bulk. But the transmission technique is actually well suited to what we're trying to do here. It was just a question of making samples that are the appropriate thickness, which are the order of a few hundred to a half micron for the energy ranges we were interested in. And sample prep is always an issue, and you will see that the content of this part of the talk on the zinc ion batteries was very much an issue of feeling our way to get the optimal sample preparation. So the next step is write a proposal. What I'm telling you is if you really want to win in the proposal game and really be well prepared for a STXM experiment, you really need to think quite a bit about what information that is going to be relevant to the question you're asking, and then how do you actually get that by making a STXM measurement. So by thinking of all that beforehand, it's much easier to ask the type of questions that the proposal document requires. That is, how are you going to make your measurements? How many measurements do you need? What's the sensitivity that you need? And if you're looking for 1 part in 1,000 on average in a sample, unless it's very concentrated, you may not see that. And of course, there's also many other ancillary things that Karina briefly mentioned, anything to do with hazards, biochemical, electrical, etc., has to be proved, and various things like that. So just a little bit more about this project. In fact, you can see an argument going on in the literature about the active electrochemical processes going on. The side of that argument that the group I'm working with sits on is that they're basically seeing the process of one where the zinc 2+ ion acts very much like a lithium ion in a lithium battery. That is that it intercalates, it enters inside the structure of a host transition metal oxide, in this case manganese dioxide. And so doing, it changes the oxidation state. So in lithium iron phosphate, for example, which is STXM has been used to study it quite a bit, the iron phosphate goes from an iron 2 phosphate to an iron 3 phosphate as the lithium ion goes in. So the lithium ion does not change its oxidation state, except on the anode, but in the cathode of a lithium battery, it's all about oxidation state changes in the host transition metal oxide. So here we're using a particular phase of manganese dioxide, which has channels in it, tunnels, which are the appropriate size for zinc 2+ ions to enter. Zinc metal is used as the anode. Zinc sulfate, is the transporter for the zinc 2+ ion in the electrolyte, and there's a separator to prevent shorting. So the hypothesis is that when you have a charged battery, a zinc ion battery, and it is used to discharge to drive a current in an external circuit, the MnO2 is being reduced because as the zinc 2+ intercalates, you reduce the manganese 4 to manganese 3. And simultaneously at the anode, there's oxidation of the zinc metal to the zinc 2+. And so that reaction can be symbolized by that chemically, but of course it's split into 2 half reactions. And then in the charging mode, we have electrons from the external circuit, which oxidizes back up the manganese 3 to manganese 4, and simultaneously some of the zinc 2+ ions are reduced to zinc 0 at the anode. And really, part of the question that we're going to be able to address is how reversible at a given state of use of this battery is the chemistry. Because as you degrade the battery, the number of amp hours that the battery is capable is reduced. And again, within our picture of what this battery is doing, the reason that's happening is that it is not a simple manganese 4 to manganese 4 to manganese 3 oxidation state, but you get disproportionation of the manganese 3 to some manganese 2, which is no longer a reversible component of the redox chemistry that's going on. So those are the things we were looking for based on our understanding of the operation of the battery. So the next question was, or some of the questions that are going to be arising with respect to getting ready for this STXM is, how are we going to make our samples? That's obviously very specific to the specific type of science that a STXM might be applied to. And sometimes it may be a number of months between when you make a sample into its relevant form and when you'll be able to get it into the STXM. In which case it's important to think about things like, is your sample subject to oxidation or other changes by exposure to oxygen or water? How would you store it to prevent that, etc.? I have a long, a 10-page slide thing on various ways of preparing samples. I don't want to go into that level of detail here, but if anybody is interested, I'm more than happy to share that. Of course, in science, it's good always to do complementary measurements. And so most cases, people are coming to the STXM with having done some other imaging and or spectroscopy of the material in order to define the question they're asking. Almost always that will include optical microscopy. One way of thinking about STXM is it's, in a way, just a better high resolution optical microscope. And of course, electron microscopy can play a role. Again, that depends very much on the project. So as Karina said, there are various ways of putting your sample into the STXM, either on a TEM grid or full 3mm grid, or these half grids for focused ion beam preparation of samples. You can attach them to this 6 or 8 hole plate in various ways. I personally, with grids, like to tape them from the top with single-sided tape because it's very easy to remove that and retain your sample. Some people like using very sticky carbon tape, double-sided sticky, and it's impossible to get that material off without completely mangling your grids. Nail polish, I know the Max 4 team likes to use that and uses it very successfully. So there are a bunch of ways. Trial and error never hurts. Silicon nitride windows are a bit trickier. Taping them from the top usually doesn't work. They slide around too much. So you're ending up using something like double-sided tape from underneath or an adhesive at the edges. One thing that's really critical that I like to emphasize is that if you don't really have a good way of visualizing your samples before you start the experiment, you very easily waste an awful lot of time. First of all, having to do some additional optical microscope characterization at the STXM beamline. It's a very beautiful microscope to do that, but every time you've got your sample under that microscope, you're not using STXM. And more importantly, if you look carefully at your optical microscope, very often you can see hints of what the chemistry or the modifications of the sample that are going to give you the clues as to what's going on in your sample. And you should be prepared to spend quite a few hours on optical microscopy. And I'll just show on the next slide some of the things that came out from that optical microscope examination of this particular sample we looked at Max 4. I'll go to that in a second, but it's also important, you're going to be moving fast, right? You're going to try to make use of every minute that you have access to the STXM. And if you're not organized, it's very easy to make mistakes, confuse different samples. So I really insist that before we go into any session at a STXM, that we have a detailed description, coding for each sample, some description of what it is, what our targets are in terms of measurements, what our scientific goals are, et cetera, et cetera. You also should plan on having a few more samples than you absolutely need, because things sometimes go wrong. You can't do a particular edge for some reason, or your sample prep didn't really work the way you thought it was. So it's always good to have maybe at least 50% more samples than you could ever hope to do within the time of the STXM, because some things just don't work out. So this is an example of what I learned did the optical microscopy visible light microscope preparation for the sample that I did study a couple of years ago at Max 4, which was sort of a breakthrough study. And this is a low resolution optical microscope. You can see that there are 1, 2, 3, 4, 5, 6 sections, microtome sections. So the outer part of this is epoxy. The center is an extract from the battery, which I'll tell you about in a second. And then we're going in finer detail. And after looking at all of these, I felt that this one actually had the morphology I was expecting from the way we prepped the sample. So this is then an expansion of it, and then an expansion some more. And it's only when we went up to 50x magnification that we started to see the nature of the sample. And it turns out these yellowish regions here, and we confirmed this by the STXM, are actually the manganese oxide cathode material, and the black materials here are actually the carbon support that it's using for electrical contact to the outside world. And what we're interested in is exactly that interface between the carbon and the manganese dioxide, or one of the interests. And these gray areas here are most likely a mixture of the two, which we would only find out when we do the STXM experiment. So I want to just sort of say, compare two different approaches that we did to measure this system, and it's a bit of a lesson there. So these measurements, these samples were made by members of Drew Higgins' group using a coin cell. So you've seen these, they're the way that you can get lithium and other battery technology for various devices. And it's a stack of various materials, the zinc anode at the bottom, you have the carbon electrical contact of the cathode, and then this manganese dioxide material intermixed with the carbon black. There's a glass fiber separator, and the whole thing is compressed to get good electrical contact and be able to do electrochemical testing. So in this particular sample, because we had success with preparing simply by scraping the electrodes off a supercapacitor electrode in a previous study, we thought we'd start with that same process. And so here is again an optical microscopy image. This particular square, you can see there's a fold over of some of the material, sport material, but also these little spots. This is now a STXM image. We see the fact that there are spots there, but nothing more. And then as we go in using the higher resolution STXM, we see that there has some morphology there. So that's good. However, when we went in detail to try to map the manganese oxide materials that were present there, we found out that most of that region that was studied in detail in this green box is actually just the carbon material, graphitic material for contact, and it was only these small regions that really contain the manganese. And in this particular case, which was the as-made fully charged battery material, they're all in the manganese 4+ state. So yes, that in some sense confirms that, but we have so little oxide material there, it's not very much of a convincing story. So having done several tries at this at various synchrotrons, we decided that we would really go back to the tried and true method of embedding and microtoming. And so here we wanted to focus on the cathode material, the manganese dioxide. And what we did then was we peeled off the upper part of this structure, the glass fiber separator and the anode, but left the rest of it, the carbon black and the manganese dioxide intact, and then embedded that in an epoxy and microtomed it. So again, this is that material. It's the same slide as a couple ago. So we went in and with the STXM looked at this area, which was at the interface between the carbon and the manganese dioxide, several magnifications. And then we started to do the spectroscopic measurements, looking at below the manganese edge and on the peak of the absorption of all of the manganese oxides. The difference of that, what we call a stack map, just very nicely shows you the spatial distributions of the manganese present. We then went in on a smaller area where we could then do a full stack where we can trace out and see the spectroscopic differences between with manganese 2, 3, and 4 oxidation states. This is a color-coded composite of the maps that were derived from that full manganese 2p stack, such that we can tag each pixel as either pure manganese 4, original material, or the manganese 2 material, which is highly degraded, and then there's still small amounts of this manganese 3. This was actually up here, the 94 cycles. So typically by 50 cycles, they're pretty useless as batteries. So this was a fully degraded cell that was not making very much difference between charge and discharge in terms of its potential. And it was left in the discharge state. So that's consistent with the chemistry going from the intercalation driving conversions from manganese 4 to manganese 3 and back to something where the manganese is no longer in a state where it can actively participate. We did try a third way, most recent measurements. It was similar to this, but we were ambitious and tried to see also the zinc anode and the glass fiber separator. But these two materials are so hard that when you try to microtome the material, they basically get stuck onto the diamond knife and pull out, so that they warp the structure of the material. So that wasn't very successful. Okay, so just a little summary. This is what I put back to the Max 4 as a report of this study that we did in 2023. And basically a lot of what you've seen, that we could characterize this degradation in terms of multiple oxidation states. The reason I'm showing this particular slide is that one of the challenges that you may encounter, particularly if you're looking at polymeric or biological materials, is radiation damage. The STXM X-ray absorption technique has very meaningful, significant advantages relative to electron microscopy, particularly electron microscopy with electron energy loss spectroscopy, but it still does radiation damage. So my group has done a lot of quantitative studies of that, and roughly of the order of 100-fold advantage in terms of the dose the sample will tolerate before you get similar amounts of radiation damage. And so this is what you see here. The dark line at the top is where the beam sits for a slightly longer time, because it's got to accelerate from 0 velocity. And this system, the beam is scanned downwards repetitively, so the vertical scans of the sample. And this darker line is identifying the starting point of the imaging. It probably did not seriously affect the chemical analysis, but it is something you have to be aware of. And one of the things that is important is that because we use a rectilinear scanning, most STXMs do, you actually can identify modifications caused by radiation damage because they match the actual analytical measurements they're making. So just one other point, you don't have to only use the one edge you target. And in this system, it turns out that the oxygen 1s is as able as the manganese edge to differentiate the oxidation states. So this is something to keep in mind, particularly when you're going into a project. It's really useful to think broadly about the sample and maybe do some exploratory measurements at other edges, which may reveal something interesting, even though that's not how you've initially planned the measurement. Okay, I'm going to stop there. I have a few more slides to deal with, I think, some things that Martin might be talking about, but why don't we pause here for a possible discussion.